Consider this as an axis, and suppose there is a distribution of particles around this axis. Assume this one is m1, which is at a distance r1 from the axis, m2 at a distance r2, m3 at a distance r3, and so on. Okay, there could be any number of particles. We know its total moment of inertia about this axis is given by sigma mi ri square, which is basically m1 r1 square plus m2 r2 square, so on up to mn rn square. The idea is that total moment of inertia of a system is the sum of moments of inertia of each particle of the system. Okay, fine. Now, suppose you shift one of these particles, let's say m1 itself, you slide it parallel to the axis and bring it here to this position. Remember, you are sliding it parallel to the axis. Okay, so you are not taking it closer to the axis, you are not taking it farther from the axis also. You are moving it, but it's at the same distance from the axis. Then one of you tell me, if this kind of sliding is done, will it change the moment of inertia of this system?
No, sir.
Definitely not. Okay, if we slide the mass of a system or part of the mass of a system, this is an important property, that's why I'm spending some time on it. Part of the mass of a system parallel to any axis. Okay, see clearly the distance of m1 from the axis has not changed. It's still r1. Okay, so its moment of inertia would not change. Then the total system's moment of inertia also would not change. So if we slide the mass of a system or part of the mass of a system parallel to any axis, the moment of inertia about that axis would not change. Remains the same. Okay, so consider this system itself. This was a system of 5 particles. Okay, let's say there were 4 particles, m1, m2, m3, and m4. Now what you can do is, you can slide all of them parallel to this axis and bring them onto one line if you'd like to. Okay, you can place m2 here, m3 here, and slide m1 to this position and m4 to this position. Okay, just to make it more comfortable to deal with, that's all. Even if you slide like this, okay, it would not affect the total moment of inertia of the system. Okay, now last class or the class before that, we had solved a problem. Yeah, this one. You are given a rod of mass m length L and an axis which is inclined at an angle alpha to the rod. Axis is passing through one end, but it's inclined at an angle alpha. We did something and we found out the moment of inertia of that rod. I mean, we integrated and we derived the moment of inertia of that rod. Okay, this is what was given to you, rod of mass m length L. Now, why were we not able to derive the answer directly? Because we didn't derive any formula of moment of inertia of a rod about an inclined axis like this. Okay. Now we just discussed one idea. If you slide the mass of a system parallel to any axis, this is the axis that I'm talking about. It's very important to keep the axis in mind. If you slide particles or total mass of a system parallel to any axis, its moment of inertia would not change. Now, when we derived the moment of inertia of this rod about this axis, we proceeded using integration. But before this derivation, we had derived this result. For a rod of mass m length L, about an axis passing through one end perpendicular to the rod, Can any of you recollect and tell me how much is the moment of inertia about this axis?
ml square by
ml square by 3. Correct. So if the axis is perpendicular to the rod, we already know the answer, or we have a formula for it. In the given problem, this one, the axis was not perpendicular to the rod. Now, we'll make use of the idea that we just discussed. If we slide mass parallel to an axis, its moment of inertia should not change. So what we will do is, we will imagine this rod as a collection of elements like this. Okay, for example, I'm highlighting some of its mass in green. You can drop that mass here. Okay, similarly, some mass is already highlighted in orange. You can drop that mass here. I mean, we are only sliding the particles of the rod parallel to the given axis. Okay, the axis is the gray line, as you can see, and I'm sliding them parallel to the given axis so that I put all of them, okay, such that we finally get all of them on this perpendicular line. Okay, so every element of the rod, we'll just slide it parallel to the given axis and drop them onto this perpendicular line, and so on. Okay, the first element is already on this line. So what we are just doing is we are sliding mass of the system parallel to the given axis. Now, if you slide mass of a system parallel to given axis, moment of inertia does not change. Fine. So imagine dropping all the mass of the rod onto this perpendicular line. Effectively, what you get is another rod like this. Are you all able to visualize this or not? The small masses of the given rod, the original rod, being dropped onto a perpendicular direction like this.
Sir, but then won't the alpha angle like become change? Won't the angle alpha change? Then what's the point of doing that?
Let alpha change. That is, see, we are trying to make it simpler, no? To solve it in a different way. Why should alpha be kept as alpha? We are not disturbing the system. Okay. What we are still finding out is the moment of inertia of this rod only. We are using some other idea to do it. Okay. And what we are doing, what is the idea that we are applying? We are dropping parts of the rod onto a perpendicular direction, because while dropping a part perpendicular like this, like when you shift this green mass here, you are not taking it away from the axis, you are not bringing it closer to the axis, you are keeping it at the same distance. So nothing wrong in doing that. Same thing, you dropped this orange mass here. Okay, you only slid it parallel to the given axis, no? You didn't bring it closer or farther, so you are not changing the moment of inertia. Same has been done with the yellow element. Same will be done with every other particle of the rod. So what we are doing is we are changing the given system to a new system, which we are sure will have the same moment of inertia as the original system. Why? Because the new system, this is the new system, this is the original one. The new system has been formed by sliding particles of the original system parallel to the axis, which should not affect its moment of inertia. Is this clear to all of you? Rishi, did you understand?
Yes, sir.
Vanilla, is this clear?
Yes, sir.
Okay. Yusuf, did you understand?
Yes, sir.
Right. So this new rod will have the same moment of inertia as the original rod. Now, why are we so interested in this new rod? Because for this new rod, the given axis is an axis passing through one end perpendicular to it, for which we already have a formula. That is why we are doing all this. So basically, we are changing the given system, or we are changing the shape of the given system to something new whose formula we already know. Okay, but we need to be careful here. The original system's mass was m. Since you just dropped all its particles onto that horizontal line, the new system's mass will also be m. But can one of you tell me what is the length of this new rod that is formed? It's clearly not the same as the original rod. How much is the length of this new rod that is formed?
L sin alpha, sir.
L sin alpha. It's like the x component of L. L makes an angle alpha with the y-axis. So x component will be L sin alpha. Okay. So the new rod that we formed is a rod of mass m, but length is L sin alpha, and the axis is passing through one end perpendicular to it. Now for an axis passing through one end perpendicular to the rod, the formula for moment of inertia is ml square by 3. But now the mass is m, L is L sin alpha. You square that and divide by 3. You get ml square by 3 sin square alpha, which is the same answer that we got the other day also by using integration. Ml square by 3 sin square alpha. Okay, so let me explain the idea once again. This is the logic that we are using. Suppose there is a system and let's say there is some axis about which you want to derive its moment of inertia. The idea that we have just applied is if elements of a system, elements means particles, if particles of a system are moved parallel to any axis, okay, like M1 is moved like this, sorry, M3, okay, M1, this was M1, and M2 is moved like this, M3 is moved like this, M4 is moved like this, they are all moved parallel to an axis. So you are not bringing them close to the axis, you are not taking them farther from the axis. They are kept at the same distance. Only the arrangement is changing a little bit. But if you do this, the moment of inertia will not change. Why? Because the distance of M1 from the axis is still R1. The distance of M3 from the axis is still R3. You are not changing the distances, so moment of inertia will not change. Okay. So the idea is that if we slide the mass of a system or some part of mass of a system parallel to any axis, the moment of inertia about that axis remains the same. We applied that in this case. You were given a rod which makes an angle alpha with the which makes an angle alpha with the axis. Fine. So what we did is we slid all the mass of the rod perpendicular to the axis. Okay, wait, I should not say it like that. We slid the mass of the rod parallel to the axis such that we form a new rod which is oriented perpendicular to the axis. Okay. Now, if you slide mass of a rod parallel to the given axis, its moment of inertia will not change. That means this original rod and this new rod will have the same moment of inertia. And for the new rod, the given axis is an axis passing through one end perpendicular to it, for which we already know the formula. And we use it, we get the answer. But this ml square by 3, I is equal to ml square by 3, is valid for a uniform rod, isn't it? What we considered first was uniform. Almost all systems we considered uniform only, for which we derived the formulas. What is the guarantee, or are you sure that this newly formed rod is uniformly distributed? Can any of you comment on this? Do you think all elements of the newly formed rod will be identical, or will there be more mass falling in one place and less mass falling in another place?
Sir, ideally it shouldn't be like that.
Like what?
Like it should be the same. Like whatever is
Correct.
falling.
Correct. It will be the same. The original rod was a uniform rod. Then you are sliding all of them parallel to the axis. So what can we say? All the particles were identical, no? Identical particles are lying on this newly formed rod now. So the newly formed rod will also be uniform only. So using the formula ml square by 3 is valid here, but its length is L sin alpha. So the answer is ml square by 3 sin square alpha. Okay, let's apply this to some other systems. Let's say there is a uniform hollow cylinder. Uniform hollow cylinder is something like a tube only. Okay, so you can consider it like this. Just a moment. Okay. So let's say there is a tube like this. So one of you tell me what kind of mass distribution is a hollow cylinder? It's an open tube, open at both ends. What kind of mass distribution is this? Linear, aerial, or volumetric?
Aerial.
It's an aerial mass distribution. Mass is spread only on the surface. Correct. Okay. Now we need to derive its moment of inertia about its own axis. Own axis means it will be parallel to the cylinder passing through the center of the face. So we need its moment of inertia about this axis. Right. Any idea, anyone, what can be done? Let's say its mass is m, radius is r. If required, you can take its length also to be L. How will you derive the moment of inertia of this system about that axis? Okay, I got one answer as mr square. That is correct. Vanilla, why is the answer mr square?
So because every particle on the hollow cylinder is from a distance r from the axis in rotation.
Okay, correct. All particles of this hollow cylinder are at the same distance from the axis. Okay, you take this particle, it's at the distance equal to radius. You take this particle, it is at a distance equal to radius. Okay, and the same happens everywhere on the surface. From the axis, the perpendicular distance is the radius itself. So we can say that the entire mass of this cylinder is at a distance r from the axis. Therefore, its moment of inertia about that axis should be mr square, because moment of inertia only depends on mass and the distance at which the mass is present. Okay, are you all able to visualize this or not? As I said, this is like a tube, an open tube. Okay, now if you imagine an axis through the center of the tube parallel to it, every element of the tube will be at the same distance from the axis, and that distance is the radius itself. Therefore, the entire mass m is at a distance capital R from the axis. So the moment of inertia will be capital M r square. Any doubt in this? Okay, fine. Just a moment. In case you are finding it difficult to visualize, basically this is what is a hollow cylinder. Okay, and how is the axis passing? Assume this is the center of the face of the cylinder. It's passing through the center like this. So every element of the cylindrical surface will be at the same distance from that axis. Okay, so the answer is mr square. That's fine. But there's another way also you can derive this. Of course, this is the easiest way. All mass is at the same distance, so answer is mr square. Okay, but there's something else also we can do. What did we just learn? If you slide mass of a system parallel to an axis, it won't change the moment of inertia of the system. Okay. Now you can see the axis, that yellow line. Imagine compressing the cylinder along the direction of that yellow line. Okay. Imagine compressing the cylinder this way, all the way down to the base. What does it form? Or what does it change into? Rishi, what do you say?
Sir, the mass will decrease and the radius will increase.
Why will mass decrease? Where will mass go? If you just compress something, it will become lighter. What
No,
are
no,
you
no,
saying?
no.
Huh?
Radius will decrease, sir.
Why will radius decrease?
Sir, because it's being compressed, so the
We are not compressing it this way, no? Sideways. We are not squeezing it in like this. Okay? We
so
are.
if the force is from upward, they'll increase.
Why should it go to the sides? I mean, why should it increase? Okay. See, maybe in a real life situation, when you try to crush a water bottle or a can, some particles may come in, some particles may go out. Okay. Now we are imagining something ideal. Just visualize every particle of this cylinder simply being slid down parallel to the y-axis. Then in that case, what happens? It becomes like this. Okay. Or I can say it becomes a ring. If you just slide all the particles down, you will get a ring like this. Are you all able to visualize that or not? Yusuf, what do you say?
Yes, sir.
Okay. Rishi, are you convinced?
Yes, sir.
Fine. Now the mass would remain the same because we kept all the particles there itself. We didn't remove any particles from the system. So mass of the ring is still m. Radius is still r, same as that of the cylinder. Okay. Now the moment of inertia of this cylinder should be the same as the moment of inertia of this ring now. Because we only slid mass parallel to an axis. We didn't bring it closer to the axis, nor did we take it away from the axis. So it becomes a ring whose mass m is m, radius is r, and the axis of the ring is same as the axis of the cylinder. And we already know what is the moment of inertia of a ring about its own axis. It is mr square. Okay. For this ring about this axis, if it is mr square, then for the cylinder about that axis also, it will be mr square itself. And that's what we expect it to be. So for a hollow cylinder about its own axis, the moment of inertia is mr square. Is this clear to all of you? Any doubt in this? There is also another way to derive. You can treat the hollow cylinder as a collection of rings. But there's no point. You'll have to split it into small rings, integrate and all. Okay. Someone is saying. Okay, Pawan, that's fine. I'll send you the recording. Okay. Next. Suppose there is a uniform solid cylinder of mass m, radius r. Solid cylinder means it is completely filled with mass. Consider it like this. Its mass is m, radius is r. And you need to derive its moment of inertia about its own axis again. Own axis means this one. Okay. Can any of you, not can any of you, follow the idea or use the idea that we discussed today? Imagine this solid cylinder being compressed or being compressed parallel to the axis. Imagine what it changes into and then derive the moment of inertia of that shape. Those of you who were there in the last class should definitely be able to answer. Those of you who know moment of inertia earlier, I mean already, you should also be able to answer. Try. Yeah, Aishwarya, Vanilla, your answers are correct only. Yusuf, if we compress this solid cylinder parallel to the axis shown, what does it change into? Imagine you compress it completely. What does it change into? It becomes a disk, correct? Okay, let's visualize that disk. Now this is a solid cylinder, no? So if you compress it, you get a disk like this. Mass will be there everywhere on the disk, right? And the axis that you are given, the own axis of the cylinder, also becomes the own axis of the disk. Now this disk's mass will be m itself, because we didn't remove any mass from the cylinder, we just compressed it. And its radius will also be r itself. And for a disk of mass m radius r about its own axis, the moment of inertia we derived yesterday, it is mr square by 2. But this is valid only for, this is valid for sure if it's a uniform disk. Okay. Now this is a uniform solid cylinder, no? And like you visualize its base, the base is in the form of a circle. The boundary of the base is in the shape of a circle like this. Now, at every point on that circle, there is an equal amount of mass. You can visualize tubes of mass present like this. Like this. So mass extends up to the same height everywhere, right? So if you compress the cylinder and make it a disk, the disk that you get will automatically be uniform. You won't see more mass falling at some points on the disk and less mass at other points. Okay. Therefore, this assumption is valid. And the answer is mr square by 2. Okay. So remember, hollow cylinder about its own axis is like a ring about its own axis. Solid cylinder about its own axis is like a disk about its own axis. Next. Now, yesterday's class, we kind of, okay, this was easy only. Yesterday's class, we derived the moment of inertia of a solid sphere. Whose mass is m and radius is r. What did we do? We treated the solid sphere as a collection of hollow spheres, shells. Okay, because we had already derived the moment of inertia of a shell, we used it. That's fine. And we wanted the moment of inertia of the solid sphere about an axis passing through its geometrical center. That's what we derived in the last class. Okay. Now let's use this compression idea here. If you compress the mass of a solid sphere parallel to this axis, can one of you tell me what it becomes? Just squeeze a solid sphere onto one plane. What does it become? It becomes a disk itself. Okay. So you can visualize it like this, all the mass being slid parallel to the axis. What you get will be a disk like this. Okay, I have changed the color. Never mind. Okay. Now we didn't remove any mass from the sphere. So this disk's mass will also be m itself. And its radius will be r itself. That is the radius of the sphere. Then can we say that the moment of inertia of this system is mr square by 2? Because when you compress a sphere also you get a disk only, and disk about its own axis is mr square by 2. So can we say the sphere's moment of inertia is mr square by 2? Anyone?
No,
Aishwarya, why not?
sir, the mass will not be distributed uniformly.
The mass will not be distributed uniformly. Correct. When you drop all the particles of a sphere vertically downward, you will clearly see a lot of mass falling close to the center. Okay, but there will be very little mass, maybe only this much, falling near the edges. So the disk that you get, the shape is a disk only, but the disk that you get will not be a uniform disk. It will have more concentration of mass near the center, and as you go towards the boundary, the concentration of mass will decrease. Okay, so the solid sphere's moment of inertia cannot be derived this way. It's not mr square by 2. Okay, and we did the derivation yesterday. We got it as 2 by 5 mr square. That answer is correct only. Okay. Fine. So remember this idea about moment of inertia. You can slide mass of the system, the entire mass of the system or some parts of the system parallel to any axis that won't disturb its moment of inertia about that axis. Because when you slide particles parallel to an axis, you're not bringing them closer to the axis, nor are you taking them farther from the axis. So that won't affect the moment of inertia. Okay. Now, let's quickly go through all the cases in which we have derived moment of inertia starting from the first day. Now, one of the cases in which we derived the moment of inertia for a rod is this, about its perpendicular bisector. Perpendicular bisector passes through the center of the rod. Okay, and about that axis, we know it is ml square by 12. Fine. Yesterday's class, we derived moment of inertia first for a ring about its own axis. Now see, the own axis of a ring also passes through the center of mass of the ring. The geometrical center itself is the center of mass. Okay. Next, we discussed or derived moment of inertia of a disk about its own axis. That axis also passes through the center of mass of the disk, because geometrical center itself is the center of mass of a disk. Next, uniform hollow sphere. Also, we derived moment of inertia about an axis passing through center. That point is the center of mass. For a solid sphere also, we did the same. Axis passing through the center, and for solid sphere, that point is the center of mass. Even today, hollow cylinder, solid cylinder we considered. For hollow cylinder and solid cylinder also, their own axis passes through their center of mass. Okay, somewhere inside there will be a center of mass. The axis will be passing through it. So basically what we have done is, using the fundamental ideas of moment of inertia, we derived the moments of inertia of some regular shapes through axis passing. Wait, let me rephrase this. Using the fundamental ideas of moment of inertia, we derived the moments of inertia of some regular shapes about axes which pass through their center of mass. But moment of inertia of a system can vary from axis to axis. And for a given system, you can imagine infinite different axes. For example, this solid cylinder itself, about this axis, we got it as mr square by 2. But if you take an axis somewhere here, the moment of inertia will be something else. If you take an axis somewhere here, the moment of inertia will be something else. Okay. Now you can't keep deriving the formula from the fundamentals about every axis that you need. Okay. So what we are going to do is, this moment of inertia about an axis passing through center of mass, which we have already derived, we will make use of this to derive moments of inertia about some other axis. Okay. For that, there is a theorem that we can use. In fact, there are two theorems for moment of inertia that can be used. First, parallel axis theorem. Okay, follow this carefully. These are very, very important. Moment of inertia is a, like, what can I say? One of the most important topics in your syllabus. in your final JEE mains advanced exams also, exclusive questions will be asked based on only moment of inertia. Okay, they'll give you a system and ask you to calculate its moment of inertia. It is that important. And of course, moment of inertia is also used to calculate kinetic energy, as we have already seen. And there are some other ways also in which it can be used. So this quantity moment of inertia is extremely important. Okay, so you need to know how to derive it about any axis for any system. Fine. So what is the parallel axis theorem? Listen, suppose there is a system like this, some random system I am considering. We will discuss the proof in detail. Assume this system center of mass is here. Okay. We'll just mark it as C. C is the center of mass of this system. Every system will have a center of mass, and we have already worked on that. We know how to identify the position of center of mass of a system. Fine. Suppose you know the moment of inertia about an axis passing through the center of mass. So suppose you know the moment of inertia about this axis. How is the axis oriented? I drew a cross here. That means the axis is perpendicular to your screen. Fine. About that axis, let's say the moment of inertia is ICM. Why are we calling it ICM? I is the symbol for moment of inertia. CM indicates center of mass. This is an axis passing through center of mass. So moment of inertia about that axis, ICM. Suppose there is another axis parallel to this one. Now the original axis through the center of mass was perpendicular to your screen. So the other axis parallel to that one will also be perpendicular to your screen only. Okay, I'll try to show you the show you how it looks when you see from an angle also. Let's say this is the system when viewed from an angle. So assume this is its center of mass. Then axis passing through the center of mass is this one. And there is another axis parallel to it at a certain distance from it. So maybe somewhere here. Okay. About the green axis, which is an axis passing through the center of mass, let's say the moment of inertia is ICM. What we want is the moment of inertia about the orange axis, which is parallel to the axis passing through center of mass. That's why the theorem's name is parallel axis theorem. Okay. Assume the distance between these two axes is d. In this diagram also, you can consider this distance as d. Now what I have done here is, I have taken a flat system. Flat means planar system, like a plate. Okay, just a moment. I'll take another diagram. 1 second. Okay, for better visualization, we can consider something like this. So this is a flat object that I have taken, flat lamina, okay, of a random shape. Assume its center of mass is here. So the moment of inertia about an axis passing through its center of mass, we called it as ICM. And now we want to derive its moment of inertia about some other axis. That other axis may lie within the object, it may lie outside the object also, doesn't matter. You'll understand after we derive it. But what we are trying to do is derive its moment of inertia about this axis. And the distance between these two axes is d. So from here to here, the distance is d. Now, when you look at it from above, it kind of looks like this. Fine. Let's call moment of inertia about this axis as I. Follow the derivation carefully, all of you, because this analysis is important, like how we are going to derive this. We'll be using some interesting ideas also in between. Let me just mark that one point, orange point, through which the axis is passing. And let's consider a random particle of this system, maybe some particle here. Assume its mass is m1 and its distance from the original axis about which we want the moment of inertia, let it be r1. Okay. So what we are going to do is we are going to form a vector triangle here. Let's take this position vector as r1. That is the position of the particle m1 with respect to the orange point. That is r1. Okay. And let's take another position vector from here to here. Call it r1c, position of first particle with respect to center of mass. Okay. And let's take another vector from here to here. What vector is this? This is the position of center with respect to point. Let's call this point as P, the orange point as P. Okay, now these three have formed a vector triangle. And from triangle law of vector addition, we know that if two vectors are taken as two sides of a triangle, then the closing side taken in reverse order will be their resultant. Therefore, in this vector triangle, we can write R1 vector is equal to RCP vector plus R1C vector. This is from triangle law of vector addition. Okay, now why do we care about all this? What we are trying to do is derive the moment of inertia of this system about that orange axis, which is at a distance d from an axis passing through the center of mass. We don't want to use the fundamentals. We don't want to integrate. Okay, we are using some new technique. We are deriving some new technique. Okay. Now, this particle m1 will contribute some moment of inertia I1. I1 is m1 r1 square. That's the basic formula for moment of inertia of a particle about a given axis. The particle m1 is at a distance r1 from the axis. Therefore, its moment of inertia will be m1 r1 square. Similarly, other particles, I2 will be m2 r2 square and so on. I of the nth particle will be mn rn square, and we know this. Okay, but now we will use some ideas of vectors. Can one of you quickly tell me what is the basic formula for A dot B?
AB cos theta, sir.
AB cos theta, correct. Magnitude of vector A, magnitude of vector B, cos of the angle between them. Then what will that dot product of a vector with itself be? Okay, Vanilla, don't answer. Anyone else? What will A dot A be? See, both vectors are the same. Then it will be A cos. What is the angle between vector and itself? 0. Cos 0 is 1. So this simply becomes A square. Okay, a vector dot itself is just the square of its magnitude. Okay. Why do we care about all this? Now see, in moment of inertia, we have m r1 square. R1 square can be written as R1 vector dot R1 vector. Why? If you do it that way, somehow you can bring these two into the picture, into the derivation. Because we know that R1 vector is the sum of R1C plus RCP. Okay, we are trying to somehow make use of center of mass in deriving moment of inertia. Okay, or in expressing moment of inertia. Okay, so that's the idea that we are applying here. Then R1 square, which is square of the distance of the first particle from the required axis, orange one, can be written as R1 dot R1. And in R1, we will use this. We will substitute this now. Okay, so follow this carefully. Therefore, moment of inertia of the first particle, which is m1 into r1 dot r1, can now be expressed as m1 times r1 is r1c plus rcp. Again, dot r1c, that is position of 1 with respect to center, plus position of center with respect to the other point about which we want the moment of inertia. Okay, actually not point, the other axis about which we want the moment of inertia. Okay, simplify this, not simplify, multiply, you will get r1c dot r1c. That's the first term, plus r1c dot rcp, plus again rcp dot r1c also you will get. Okay, so I'll just write this as 2 times of this. Plus the last term will be rcp dot rcp. Okay, this becomes m1 times r1c dot r1c is r1c squared. It's like a dot a is a square, no? r1c dot r1c is r1c squared. What is r1c? Let's look at the diagram again. r1c is the distance of the particle m1 from the center, from the axis passing through the center. Okay, you have to square that distance. Next, we'll write the last term here. rcp dot rcp becomes rcp squared. Now what is rcp? It's the distance between C and P, the axis passing through the center, and the new axis, the green axis and the orange axis, I should say. It's the distance between those two, which is nothing but d. So rcp square can be called d square. Okay. And then the last term, 2 r1c dot rcp. We can't simplify this, so we'll keep that last term as it is. Fine. So you end up getting moment of inertia of the first particle about the new orange axis is m1 r1c square plus m1 d square plus 2 m1 r1c dot rcp. This is what we get. Now if you observe, this original distance r1 is no longer part of the equation. We have converted that into r1c and rcp terms. That was our aim. Okay, we want to make use of center of mass in expressing the moment of inertia. Okay. For the second particle, the expression will be m2 times r2c, means distance of second particle from the axis through the center, square it, plus m2 d square. D is the same for any particle. D is the distance between the green axis and the orange axis. Okay, that's the same anyway. Plus this last term will be 2 m2. Okay, first term was m1. m2 r2c dot rcp. And so on. You do this for all the n particles, you get I of the nth particle is mn rnc squared plus mn times t square plus this last term 2 mn rnc dot rcp. Now you want the moment of inertia of the entire system. If you want the moment of inertia of the entire system, you will have to add all these terms. Okay. First term, that addition we will do. Second term, you observe it. m1 d square, m2 d square, so on up to mn d square. You add all of them, d square will be common. And m1 plus m2 so on up to mn becomes the total mass of the system. Therefore, the second term is simply total mass into d square. Okay. And then the last term. Last term is interesting. If you add all the last terms, you can see that 2 is common. And dot RCP is also common. Let's put them aside. What will you be left with? M1 R1C plus M2 R2C plus so on up to Mn RNC. 2 and RCP are common. So you take 2 RCP common. you will be left with dot product of sigma mi ric. Okay, m1 r1 plus m2 r2 so on up to mn rn. I'm writing it as sigma mi ri, and they are all taken with respect to center of mass. Okay. Now look at this first term also. m1 r1c squared. m1 is the mass of the first particle. r1c is the distance of the first particle from the axis passing through the center of mass. So effectively it's like mr square only, no? But about an axis passing through center of mass. Therefore, this term is nothing but moment of inertia of the first particle about axis passing through center of mass. This term is moment of inertia of second particle about axis passing through center of mass, and so on. When you add all of them, you get total moment of inertia of the system about an axis passing through its center of mass. Okay. Is this clear to all of you, all three terms, how we have added? Any doubt in this? Okay. Now let's look at that last term. There's something interesting in that last term, sigma mi ri. Do any of you remember seeing this expression anywhere? Sigma mi ri?
Center of mass.
What about center of mass? Velocity, acceleration, position?
Position of center.
Correct. Position of center of mass of a system is sigma mi ri divided by total mass of the system. Good. Now here we have that term sigma mi ri, but notice that ri is taken with respect to center of mass. Okay, like let's go back to the diagram. R1c is position of first particle with respect to center of mass. Similarly, R2c is the position of second particle with respect to center of mass. So you have these terms here, R1c, R2c, so on up to Rnc. That is what you put in the sigma bracket. So what will you end up getting? You will end up getting this bracket, like say sigma mi ri becomes total mass into position of center of mass. But you took all these vectors with respect to center of mass. So you will end up getting position of center of mass with respect to center of mass. And one of you tell me, what is the position vector of a point with respect to itself?
Zero. Sir.
0. Okay, good. Position vector of a point with respect to itself is 0. Now this sigma mi ri, what does it actually become? It becomes total mass of the system into position of center of mass. But you took sigma mi ri with respect to c. So you will get mass into position of center of mass with respect to center of mass. And position of center of mass with respect to center of mass is 0. Therefore, that last term becomes 0. And we now have the result. Moment of inertia of the system. About which axis are we taking? About that orange axis. Remember the axis. Okay, which was parallel to the axis passing through center of mass. Fine. So moment of inertia of the system about the orange axis is equal to moment of inertia of the system about axis passing through center of mass plus total mass of the system into square of distance between the axes. This is the theorem, parallel axis theorem. Okay, so like proof, you can go through it later also, but see, what all do you need to know to apply this theorem, or where can you use this theorem? As I said before we started the derivation, we have derived moments of inertia of various shapes about axis passing through their center of mass, right? So you should know moment of inertia about an axis passing through the center of mass, and you should, and if you need to find moment of inertia about another parallel axis, like the one shown in this diagram, then you can use this theorem. Why is it compulsory that they are parallel to each other? Why can't they have some other angle? That is because if the axes are not parallel, what can we say? the distance is this, what do you call, vector triangle cannot be drawn. Actually, it's hard to make you visualize. Anyway, for now, you just remember it has to be parallel. Otherwise, writing it this way will not be valid. Okay. I'll try to draw a 3D diagram and explain it to you in the next class, why the axis must be parallel. Fine. So if you have two parallel axes, one of which is passing through the center of mass, then you can use this theorem. And here, while deriving, I took help of a flat system. Okay, why did I take a flat system? If I consider a particle here, the line joining the particle to the orange dot, green dot, and the line joining green and orange also, these three will form a triangle in the same plane. I use triangle law of vector addition, no? Okay, they form a triangle in the same plane. In fact, any particle of this system that I take will be in the same plane formed by these three. Okay, connecting these three dots. Okay, does that mean parallel axis theorem is valid only to a planar system? No, parallel axis theorem is valid to any system. Okay, you can have a three-dimensional system also. Now, we just discussed one idea today. Suppose this system itself was three-dimensional. Instead of being flat like this, just a moment, I'll copy that. Okay, this is how we took it. Suppose this system was actually a three-dimensional system like this. Okay, as I said, it's hard to show here. Okay, let's say it's a bulk system. You can still compress it parallel to an axis and make it a flat system, no? So imagine it was done like that. For the sake of proving the theorem, imagine the system was compressed parallel to the green axis. Now, if you compress it parallel to the green axis, then you get a plane perpendicular to the green axis. So this flat surface is a plane which is perpendicular to the axis. That doesn't mean parallel axis theorem is valid only to flat surfaces. It is valid to any valid for any object. Okay. Just to prove it, you can compress it into a flat object and prove. Now, let's make use of this. Moment of inertia of the system about any other axis is equal to moment of inertia of the system about a parallel axis passing through center of mass plus total mass of the system into square of the distance between the two axes. Remember what is d also. D is the distance between the two axes, one of which is passing through the center of mass. Okay. Fine, let's consider solid cylinder itself to start with. Suppose there's a solid cylinder like this. Assume its mass is some 10 kg. Radius is 2 meters. Okay, it's a very large cylinder. 2 meters is a significant distance. Okay, roughly your height. Okay, now what I have drawn here is the own axis of the cylinder, but that is not the one about which I want the moment of inertia. I want you all to derive its moment of inertia about this axis, which is at a distance of, okay, clearly greater than the radius. So maybe 3 meters from the axis passing through the center of mass. Derive moment of inertia about this new axis, all of you. I got 2 answers. Okay, I think they are correct only. We'll just wait for 1 minute. Others also derive quickly. Okay. Rishi, how are you trying to solve this? No response. Yusuf, any idea? If you can unmute. No. Okay. Fine. See, the given axis about which you need to find out the moment of inertia is parallel to an axis passing through the center of mass. Okay, these two are parallel axes, the green one and the dotted black one. They are parallel, and the distance between them is given 3 meters. Okay, the black one is an axis passing through center of mass, and we already know the moment of inertia of a solid sphere about this axis. So it's like ICM is known to us. What is the formula? It's not solid sphere, sorry, solid cylinder. What is the formula? mr square by 2. We derived today itself. ICM is mr square by 2, and the distance d between the axes is 3 meters. That's all. Therefore, I becomes, the formula is ICM plus md square. ICM is mr square by 2. Mass is given as how much? 10 kg. Radius is 2 meters. So 10 into 2 square by 2 plus mass into square of the distance between the axes, 10 into 3 square. 1, 2 cancels, 10 2 is 20, plus 9 into 10 is 90. The answer is 110 kg meter square. It's a direct application of parallel axis theorem. Okay. Next, we'll just verify one of the results we have already derived. For a rod, about its perpendicular bisector, we already know the moment of inertia. Like we already know the formula for moment of inertia. Assume the rod's mass is m, length is L, uniform rod. Then this axis moment of inertia is ml square by 12. And about an axis passing through one end perpendicular to it, it is ml square by 3. These two results we derived from the fundamentals. Okay, but you can notice now that these two are parallel axes with one of them passing through the center of mass. This can be treated as ICM now, and let's call this as I. Let's just check if the theorem is valid or not. One of you quickly tell me what's the distance between these two axes. Okay, fine, I don't have to ask you. This is half the length of the rod, so L by 2. You know, center of mass of a rod is its midpoint. So we want to check whether I is ICM plus MD square or not. Now ICM plus MD square, if you do, ICM is ML square by 12 plus MD square, if you do, M into L by 2 whole square. That is ML square by 12 plus ML square by 4. I'll write it as 3 ML square by 12. Effectively, it becomes 4 by 12, that is 1 by 3. And that is I. So ICM plus MD square is I. We just checked it in one case. Okay, next. Derive the moment of inertia . Okay, let's consider this system, disk. For a disk about its own axis, it is mr square by 2. Okay. Assume there is another axis. You know this is the center of mass and all. Let's say there's another axis somewhere here. And how far is it from the existing axis? It is at a distance, let's say, half the radius. Derive moment of inertia about this axis quickly. Mass is m, radius is r. Answer should be in terms of m and r. Vanilla, your answer is correct only. Aishwarya, correct. Saket, any answer?
Sir, MR by 2 of R plus 1
What did you say? MR by 2?
of R plus 1.
See, you can't add r and 1. R is a radius, which is a distance. 1 is just a number. So you should never get expressions like that. Anyway, what is the formula, you tell me, for parallel access theorem?
Sir, moment of inertia of center of mass plus mass into distance square.
Okay. Don't call it moment of inertia of center of mass. Moment of inertia about an axis passing through center of mass. Okay, fine. Now we know that this is mr square by 2 now. Plus mass of the disk is m. Saket, what is d supposed to be? Or what is the meaning of d?
So distance between the 2 points.
Distance between the two axes, two parallel axes. How much is it in this problem?
R by 2. Sir.
R by 2. And you have to square that. That's all. So it becomes mr square by 2 plus mr square by 4. 1 by 2 plus 1 by 4 is 3 by 4. So the answer is 3 mr square by 4. That is the moment of inertia of this disk about the given axis. Okay, so understand what this theorem can help you derive. Parallel access theorem is valid to any system. System doesn't have to be planar. Okay, but for derivation purpose, let's assume the 3-dimensional system was compressed and made a 2-dimensional system. Okay, the moment of inertia of this will be same as the moment of inertia of the 3D system. Okay, so, and how did we compress it? We just compressed it. Assume we just compressed it parallel to the original green axis. Okay, we compress all the mass this way and make it a planar system. Okay. So if there is one axis passing through center of mass and there is another axis parallel to this one, which was passing through center of mass, then you can use parallel access theorem to relate the moments of inertia about these two axes. So if ICM is known to you, you can find out moment of inertia about any other parallel axis. Okay, kind of makes our job easy to derive moments of inertia in other cases. And what is the formula? I is equal to ICM plus MD square, where D is the distance between the two axes. Okay, we applied it to some cases. We'll stop it here for today. Next class, we will discuss another theorem, which is called perpendicular access theorem. And next class, I will have to take tomorrow itself, because as I said, we are lagging behind a lot. So I'll have to cover up. So tomorrow, 1 hour class from 8:30 to 9:30 you will have. Okay, we will discuss something called perpendicular access theorem. Okay, thank you all. We'll stop it here. And after tomorrow's class, I'll send you one worksheet based on this. And see, you take any book. Okay. be it your NCERT textbook or any reference book that you follow, you will have a number of problems based on moment of inertia. Okay, start solving the ones based on parallel access theorem. At least these basic, questions based on these basic shapes you should be able to do. Okay, disk, ring, hollow sphere, solid sphere, cylinder, such things. Okay, thank you all. We'll continue tomorrow.
Thank you, sir. So can you send
And
the